Hi, everyone. Well, someone forgot to record his lecture yesterday as I speak. It's Thursday night as I'm talking right now, for me anyway. And so what I thought I would do is record a quick summary of what we talked about in class in lieu of uploading yesterday's lecture, because I really do want to have a complete set of lectures for this class. So it benefits me as well. In any case, as you'll recall, we were discussing the issue of compounds with multiple chiral carbons. And with this, we were running into examples of compounds that not only are enantiomers, but others that are diastereomers. And so we need to understand the difference here. And I'm not positive that this is the exact compound that we used, but it will do for the discussion. And so here we've got a compound with two chiral carbons. And so as you recall, that formula 2 to the power n, where n is the number of chiral carbons in the molecule, while 2 squared is 4. So that means we have a maximum of 4 stereoisomers possible. And indeed, in this case, as in most cases, when we have two chiral carbons, not all, but most, there are four distinct stereoisomers. And these are they. Now, I've labeled this one as S and R respectively for these two chiral carbons because I know how to label them. I won't expect you to be able to do that, since, as I said, it's a tremendous amount of work for essentially a binary answer. And I just don't think it's worth the trouble. But two things. First of all, I did leave some problems involving that in your OWL assignment, just so you got some exposure to that. But I don't plan to put anything like that in the exam. That being said, the great thing is once we have these two chiral carbons labeled, we can label the other 6 chiral carbons and the other 3 compounds just by comparison with this one. So if this one is SR respectively, then this one, which is the enantiomer, must be RS. And you'll notice I called it the enantiomer because if we imagine a mirror plane going between these two compounds right here, it's clear they're mirror images of one another. So these two compounds would be enantiomers, but there's another set of enantiomers that would be the SS and RR compounds respectively. And again, you can imagine a mirror plane running right down between them like that. So in this case, we have a total of 4 stereoisomers possible that exist as 2 pairs of enantiomers. And this is very common in cases of compounds that have 2 chiral carbons, whether they look like this or not. The same thing would happen, for instance, if the compound were cyclic. This one is not, but you would find the same thing. In nearly all cases, you'll find that there's 4 possible stereoisomers that exist as 2 pairs of enantiomers. And recall, we've already defined enantiomers. We've said enantiomers are stereoisomers that are mirror images of one another, so that you have a compound with 1 or more chiral carbons. And in cases where you have 2 stereoisomers that are mirror images of one another, those are enantiomers. And we also tend to call them non-superimposable mirror images to stress the fact that there's no way to put one exactly on top of the other and have all of the atoms match exactly. Just like you can't, I can't put my left hand on my right hand exactly the same so that all of the fingers line up exactly with one another. I can line up the 2 pinkies, I can line up the 2 ring fingers, I can line up my 2 thumbs, but I can't line it up so that they're different. That's because they're mirror images. This, of course, doesn't count. That just highlights the fact that these 2 hands are mirror images. So that's the case here also. There's 2 sets of enantiomeric pairs. Now, what about any other pairing you might take, like RS and RR, or RS and SS? Such pairs we call diastereomers. And by diastereomers, we mean 2 or more stereoisomers that are not mirror images of one another. And so that's where the term originates. So any other pair you might want to take amongst these 4 stereoisomers that are not enantiomers will then be diastereomers. And so again, this is by far the more common of the two possible cases that you'll see in compounds with exactly two chiral carbons. The other one is rare, and it's not something that I'm going to emphasize greatly, but I would like you guys at least to be aware of this possibility. And that's the possibility that we will cover next. Okay, so through the miracle of modern technology, I've made some changes here. And as you can see, what I've done is to change the bromine to a chlorine. And that still gives us a situation where we've got two chiral carbons. And again, notice that both of these carbon atoms are legit chiral, just as we gave the definition for chiral carbons. They're both sp3 hybridized, and they both have 4 different groups attached. But we find something peculiar. And the main sign of that, and the thing you need to look for to know when this is going to be the case, is when we have a plane of symmetry running right down the center of a molecule. And that's the case with this one over here. It's not the case with these over here. These ones are mirror images of each other. They're enantiomers, and they're also distinct molecules, which is the reason we can call them enantiomers, because they're different molecules. They're different stereoisomers. However, in this case, you run into something rather peculiar when you go to try to take the mirror image of this compound. And you can draw that if you like, but what you find is this species is not the enantiomer of this compound. It's in fact the exact same compound, because if you take either one of those, SR or RS, and simply turn it 180 degrees in the plane of your screen there, you find they're identical. So this compound over here is actually not a separate stereoisomer. That's just another way of drawing this first one. So maybe let's make that a different color. Good. So in fact, there are not 4 distinct stereoisomers in this case. There are only 3, and they exist as a pair of enantiomers, just like we had pairs of enantiomers before. And this interesting and peculiar compound, and compounds of this type that have multiple chiral carbons, but a plane of symmetry running down them, we call compounds of this type mesocompounds. And they don't show up very often, but it does happen sometimes. And the thing to understand about mesocompounds is that although they have 2 or more chiral carbons, they are as a whole, as a molecule, these are not chiral, meaning that if you were to dissolve this molecule up and do one of those polarimetry experiments, you would find that its specific rotation is 0. It's not a chiral molecule. And I know it sounds strange that you have a compound with multiple chiral carbons that is itself as a whole not chiral. But by our definitions, that's exactly the case here. Now you will be wondering, how can you know when you're going to run into a case like that? And I think the way I've set up the molecule makes it clear what you require. You need these 2 chiral carbons to share 2 groups in common, in addition, of course, to the hydrogen. Actually, I lied. They need to share all 3 groups in common, don't they? Both of them have a hydrogen, a methyl, and a chlorine. Here, a hydrogen, a methyl, and a chlorine. That's going to set it up to be possible for us to have that plane of symmetry. And again, compounds like this can also be cyclic. It's not rare, in comparison at least, to acyclic compounds, to run into cyclic compounds that are also mesocompounds. And likelier than not, you'll run into an example of that, either in the textbook or in an ALA problem. But the way you know that you're going to run into this situation is when you see that both chiral carbons have all 3 attached groups, other than each other, of course, as the same. That's going to allow the possibility of there being a mesocompound. And the way you tell if it's a mesocompound or not is if you can draw a plane of symmetry down the middle such that one chiral carbon is exactly reflected into the other. And I think you can see how both of these carbons are mirror images of one another. And indeed, you can see the same thing on our pink structure over here. That is not the case with these molecules. These molecules are not mesocompounds. They're an enantiomeric pair. So unlike in the case when we had 2 chiral carbons and 4 distinct stereoisomers that existed as 2 pairs of enantiomers, here we have only 3 stereoisomers. And again, that's not a contradiction because we said that 2 to the power n is the maximum possible number of stereoisomers. So there's still 2 chiral carbons, 2 squared is 4, and that tells us that we cannot have any more than 4 stereoisomers, but there could be fewer. And here's an example of a case where we have only 3 stereoisomers, because it turns out that one of these stereoisomers is its own enantiomer. And that's another way to think of mesocompounds. You can think of them as compounds with 2 or more chiral carbons that are their own enantiomer. And so when you go to draw the enantiomer, it's in fact not a distinct compound. It turns out to be the same compound again. And I've already given you some rules as to how you can tell when that's going to happen. So it's just something to watch out for, and it's a bizarre concept, these mesocompounds that have multiple chiral carbons, but are themselves as a whole not chiral. So the molecule is not chiral, even though it has chiral carbons. Also, just a reminder, of course, let's not forget one of the trivial cases when there's only 1 chiral carbon. And I often get asked, how can you know when you're going to have the possibility of diastereomers as opposed to just enantiomers? Well, if there's a compound with only 1 chiral carbon, 2 to the first power is, of course, 2, you just get 2 stereoisomers that will always be a pair of enantiomers. Always. There are no exceptions. So with just 1 chiral carbon, you will always and only get just an enantiomeric pair. So what that means is that in order to get the possibility of diastereomers, you do need multiple chiral carbons, at least 2. So that's pretty much the situation as regards enantiomers and diastereomers. But let's also move on to consider why all this might matter at all, right? And the answer to that is because we often run into cases where products of a reaction, even some of the simple reactions we've learned already, can have chiral carbons in them, whether or not the starting material is chiral. So let's examine that issue next. All right, so let's consider these 3 reactions. And these are examples of reactions we've already learned. So I would expect you to be able to predict these products. However, at the time, we didn't consider stereochemistry when we covered chapter 3. Now, sometimes you can start with a compound that's not chiral. Of course, 1-butene is not chiral. These 2 carbons are both sp2 hybridized, so they're not chiral. And these 2 carbons are not chiral. Both of them have multiple hydrogens on them. And if we were to take this compound and hydrogenate it, in other words, treat it with hydrogen and palladium, or perhaps nickel or platinum metal as our catalyst, our product would, of course, be butane, right? The double bond will go to a single bond and receive both hydrogen atoms. This compound also is not chiral. So that's one possibility, and that happens quite frequently, that you start with an achiral compound and end with an achiral compound. And again, the point is not this particular example. The point is to be aware that this type of thing can happen, regardless of what these particulars of the starting material and product are. The thing that you need to know is that it's possible to start with an achiral compound and get an achiral product out. However, that's not always going to be the case. It's actually also possible to start with an achiral starting material and get a chiral product out. And here's an example of a reaction like that, one that we've learned already. We talked about hydrohalogenation of alkenes. We said that you can treat an alkene with HCl, HBr, or HI, and you will get an alkyl halide out as the product. And Markovnikov's rule predicts that the halogen will go onto the more substituted carbon, because that results from the most stable possible carbocation, and the hydrogen will go on the less substituted carbon, the carbon that has more hydrogens already directly attached. So he would predict that you would get 2-chlorobutane in this case. But one thing we didn't mention at the time, since we hadn't covered stereochemistry, is that actually you will get both R and S enantiomers here. You'll get both R2-chlorobutane and S2-chlorobutane. And I'm using this notation here. You'll notice that wiggly bond there. I'm only mentioning it in case you ever run into it so you know what they mean. It's shorthand for both wedge and dot bond. So whenever you see a wiggly line like this, it means that you will get a mixture of the compound with a wedge bond where the wiggly line is and a dotted bond where the wiggly line is. That's what that means. It means you'll get a mixture of, in this case, both the R and S enantiomers. And since there's nothing governing the stereochemistry, I don't see anything unusual going on. There's no chiral catalyst. There's no enzyme here. It stands to reason that when the chloride ion reacts with the carbocation, that it can come from either above or below. Either of those can happen. And there's no particular reason either of those would be favored over the other. So I would predict with quite a high degree of confidence that you would get a racemic mixture. Remember, we've defined what a racemic mixture is. We've said it's a 50-50 mixture of two enantiomers. And that's what I would predict we would get here. So even though the starting material is not chiral, the product in this case is. And that's not something you know ahead of time or will have memorized ahead of time or know a bunch of rules to look for. It's more or less something you notice after the fact. That we've generated a chiral carbon by the definition of chiral carbon that we gave. That carbon atom is sp3 hybridized and has 4 different groups attached: methyl, ethyl, chlorine, and hydrogen. And so that's how we know it's chiral, not because of a pre-memorized set of rules. It's something we recognize after the fact. So what this shows is that it's possible to get either an achiral product or a chiral product from a reaction with an achiral starting material. And what you need to know is that both are possible, and you need to be ready for either of the two being possible. But it gets even a little more subtle than that. It's also possible to start with a chiral starting material, such as this one here. What will we call that guy? Let's call that R3-bromo-1-butene. How does that sound? Something like that. And in this case, let's suppose that we start with 100% enantiomerically pure R enantiomer. So only this compound, none of its enantiomer, pure R stereoisomer. If we do the same reaction with this one, once again, the HCl will add across that double bond. And once again, on this carbon, we will get a mixture of R and S. But remember, this carbon over here is not involved in the reaction. We learned about the addition of hydrogen halides to alkenes, and we noted that all of the other carbons that may be in the molecule are not involved in the reaction. Whatever there may be, there could be 1 other carbon, 2 other carbons, 5 other carbons, 50 other carbons, doesn't matter. Those are just along for the ride. Whatever you're given to start with, you'll just copy that over to the product. So the carbon with the bromine on it is not involved in the reaction, and therefore will remain the same. It doesn't react with HCl. And so I would expect that you would get a mixture of both of these products, but now notice that these are not enantiomers. These are going to be a mixture of diastereomers, because you'll get the compound with the bromine on a wedge bond and the chlorine on a wedge bond, rather. And you'll also get the compound with the bromine still on a wedge bond, because that's not going to change. Remember, that carbon's not involved in the reaction. So that will not react. That carbon's going to stay the same. We just copy it over into the product. But we'll also get with the compound with the bromine on a wedge bond and the chlorine on a dot bond. And wedge-wedge and wedge-dot are not enantiomers. That falls under the definition of diastereomers. So I would predict you would get a mixture of the RR and RS compounds over here. And those two, again, are not enantiomers. They're diastereomers. Now, as to the ratio of the two of them, I wouldn't know what exactly the ratio will be, nor would I expect you to. But I think it's reasonable, if we were to take a guess, to conclude that, that the mixture would probably not be 50-50. At least I would be surprised, because now you don't have a situation like this compound here, where there's nothing governing whether the halide ion comes in from above the molecule or behind it. But now you have this halogen atom, this bromine, that will effectively block one of the faces of the double bond, more so than the other. So I would not be surprised if you got a little bit more of one of the stereoisomers, one of the diastereomers, than the other. I don't know exactly what it would be, and I would not expect you guys to speculate on that either. If you absolutely made me speculate, I would not be surprised if they were pretty close to 50-50, but not exactly. I wouldn't be shocked if it were 60-40, or maybe as much as 2/3, 1/3, but I would be surprised if it were exactly 50-50. I would consider that kind of a stroke of luck. But other than that, that's basically it for the material in chapter, where are we at now? Chapter 5, at least that I plan on discussing. So that leaves us ready to go into chapters 11, 15, and 18, not necessarily in that order. So other than that, that's about it for this. I hope that's helpful, and I'll see you all in class as I speak tomorrow. Have a good day.